Alright, this video lecture is going to cover Newton's third law. It does, in fact, follow along pretty closely with your textbook section on Newton's third law. And we're just going to start by saying, by finding Newton's third law's relationship with the first two laws and forces. So the first one is Newton's first law, which describes an object's natural state. Right? It describes inertia, and it says that any object that has mass has inertia. It's a property of that object, and that inertia will have the object moving with uniform motion in a straight line, or depending on your frame of reference, being at rest unless a net force acts on it. And so that's saying that when the net force acting on an object is zero, the object will continue in a path with uniform motion straight. Newton's second law gives us a quantitative method for talking about how forces affect motion, and that quantitative relationship is that the net force, whatever it is, causes an acceleration. This is where we took into account the fact that forces are indeed vectors, which means that they will create an acceleration in the exact same vectorial direction as the net force that is applied to the object. If the net force applied to the object is zero, then of course the acceleration would be zero, and we would use Newton's first law to describe the behavior or motion of that object. But we haven't answered the question of where do forces come from. That question can be answered using Newton's third law. Newton's third law describes where the forces that we keep referring to in Newton's first and second law come from. And so we're going to start, instead of getting super technical, we're going to start by talking about some everyday observations. The first everyday observation that we want to take a look at is that a force is always applied by another object. If we consider one object a system, right, and we would consider it a spherical cow system, meaning that we would consider that object to all be one item, and we would ignore any of the individual little bits and pieces of motion happening within it and treat it as if it were just one simple particle-like object. Because obviously there are forces inside of you. Right now muscles are contracting inside of your body, causing blood to flow, but overall you consider yourself an object that is at rest, and that's because the net motion of you is at rest. So always remember to focus on that simplified perspective, the spherical cow perspective. In that case, it does require another object, an outside source, to cause motion. Some examples: it takes a horse to pull a wagon. If you stand inside of the wagon and pull on the wagon, you're not going to go anywhere. If you put the horse inside the wagon, likewise, it's not going to go anywhere if the horse has to pull the wagon. A person pushes a shopping cart. Right? If you climb inside of the shopping cart, you're going to need someone else to push you. You need a person on the outside, an outside object, to apply a force to the shopping cart. A hammer pushes on a nail, and a magnet attracts a paperclip. Right? These are two object systems where one object applies a force to the other object. And so we can come up with this general statement, which is a force is exerted on an object by another object. And so far, this should feel pretty okie dokie. So let's take the situation of the hammer and the nail. The force on the nail is exerted by the hammer. But here we go. It's not a one-sided situation, because the hammer also experiences a force from the nail. Right? The force that the hammer experiences, or the force on the hammer, comes from the nail. It's a force that happens because it's applied by the nail. Now you might be thinking, no, a nail does not apply a force to a hammer. A hammer drives a nail into the wood. But think about this. In your experience, when you hit a nail with a hammer, the hammer, which was moving before it hit the nail, suddenly accelerates to zero, meaning that as soon as it hits the nail, that hammer is not moving anymore. You swing your hand, it comes down, and you're stopped. And from what we know about forces, we know that the only way for the hammer to accelerate to zero is that a force acted on the hammer. So maybe now I've gotten you to buy in a little to this concept, so let's take a deeper look at it. Whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first object. Alright, so this is Newton's third law, and I actually like this version of Newton's third law better than the for every action there's an equal and opposite reaction, because when we think about action and reaction, we tend to think about our experience, and what we experience is the motion. And so if we get fixed up on the motion, then we think, oh, well, if I moved, then something else had to move too. But that's not the case. Think about how many times you apply a force and you're the only object that moves. Getting up out of a chair, you apply a force to the chair and the ground, but you're the one that moves. And so I don't always like the statement equal and opposite reaction for that purpose. I like the focus on the force. When one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first. So let's take a really straightforward example. See here we've got a hand and a desk. And so if you take your hand and you apply it to the edge of a desk, you're going to feel something. And what you're going to feel is you're going to feel a force. Now first let's consider, let's make your hand a red force vector, and let's make the desk a brown force vector. Alright, so that's our key. And so let's think about this. You apply your hand to the edge of the desk and you push. That means that your hand is applying a force downward toward the desk. Right? And as you do that, right, the harder you push, the more force you experience. But what do you feel? When you apply your hand to the corner of a desk and you push down, what you feel is you feel almost a painful feeling, and it's a resistance, and you feel it up against the direction that you're pushing, which means that the desk is applying a force on you, and it's in the opposite direction, and the harder you push, the more it hurts, which means the greater the force you experience. Right? The action force and the reaction force don't occur to the same object, which means that if I were going to consider what's happening to the hand, I'm going to do a spherical cow hand. Right? The spherical cow hand, what you're experiencing is you're experiencing a force in the upward direction, opposite to the direction that you're pushing. You do not experience the force that you exert on the desk. Your hand only experiences the force the desk applied to the hand. Whereas the desk, on the other hand, get it? Desk on the other hand. Right? The desk is not experiencing the upward force it's applying to your hand. The desk is only experiencing the downward force that it is receiving from you. Remember, we said it takes a force exerted by another object. The other object for the hand is the desk. Right here, this is the force of the desk on the hand. Right? And here, this is the force of the hand on the desk. We have to consider the fact that the objects that are experiencing these forces are different objects. Alright, one object is experiencing an upward force, the other object is experiencing a downward force. And we know that this force and this force are equal to each other, but they have opposite directions. And this is a really important concept to get nice and warm and fuzzy with, because this is the reason that things can still happen regardless of the fact that what you're experiencing is an equal and opposite force pair. right? They happen to different objects. So let's take another look, or a deeper look. Let's look at another situation. One of the things that's going to help you feel a little bit more comfortable with this concept is that when you think of yourself as the object, or you put yourself in the place of an object, you, the object, only feel the force that's exerted on you. So that means that when you exert a force on another object, what you feel is the reaction force exerted on you. You don't feel what you're doing to the other object. And now I know how many people are saying, yes, of course I feel it. I feel it when I hit a guy. I feel it in my hand. I feel the force that I hit the guy in the face with. But that's not true. You only feel the force that another object exerted on you, because in order for an object to experience a force, that force has to come from another object, which means that what you experience is a force exerted on you. And the only explanation for that is Newton's third law. So let's consider a situation where you've got a skater. All right, and that skater is on skates and leaning against a wall. And let's consider this is ice. Which means, what are we doing when we're adding ice? We're making it a low friction environment. And this right here, this is a wall. All right, and for no reason, Benny is adding some scorpions into the situation. All right, so what happens? You see scorpions creeping through the crawl hole against the wall. And so what do? You, which will do you this time in... what the heck, we'll do U as a force vector in red, and we'll do wall as a force vector in brown. Alright, what do? You apply a force to the wall in that direction. What do you experience? You experience a force that is equal to the force that you pushed with in the opposite direction. And what's the result? You accelerate away from the wall and move away. So how is it that you can move away from the wall without the wall moving away from you? How does that happen? Remember, you apply a force to the wall. The wall applies a force to you. This action-reaction pair only lasts as long as you're in contact. As soon as you're away from the wall, those forces are gone, and you move with uniform motion away from the wall as long as the friction is low enough that it can be neglected. So remember that it's the net force that causes an acceleration, right? And that the direction of the acceleration will always be in the same direction as the net force. So what direction did you move, right? Your acceleration is in that direction. So that means that your force had to also be in that direction, because if you pushed that way and you experienced your force, then you would accelerate into the wall, into Benny and the scorpions, and that's just not the way the world works. When you push against a wall, you move that way, which means you experienced a force that way, because it's the only way you could have accelerated from rest in the leftward direction. All right, so what that means is that the push couldn't have moved you. It's the force from the wall that actually moved you.
Please excuse the interruption. Please release all JV football players at this time. All JV football players at this time.
Okay, so now we have some questions to ask. Like, why didn't the wall move? Well, let's think about the situation. Remember that the acceleration is going to be dependent on the net force divided by the mass. And there's a few things that we can think about. All right, your mass is very small, whereas the wall's mass is very big. So let's think about this relationship between acceleration and mass that we looked at. Right? So if your mass is small, it means that your acceleration is automatically going to be larger than the wall's acceleration. Also, If the wall's mass is large, its acceleration would be small. But the other thing to consider is the fact that there's net force. Remember, your force and the force that the wall applies to you are equal and opposite. But you are on ice, which means that for you, the net force is going to be a result of the wall's push. Right? Especially if we can neglect friction. However, for the wall is literally bolted down and not on ice. Therefore, the wall's net force is going to be a result of your push and the resistance forces that the wall experiences due to its situation. So that means that the net force that you experience can be different than the net force that another object is experiencing if your total forces acting on you are different than the total forces acting on the wall. And so that means that there's a whole bunch of different things to consider when you're considering whether or not an action pair or a force pair will cause equivalent motion. And that's why I like the equal and opposite forces description or definition of Newton's third law more than the equal opposite reaction definition. Because if you say there's an equal and opposite reaction, you might start thinking that the acceleration should be equal, and that's just not the case because it's only the forces that are equal in contact. So that means that we can take a look at multiple other situations where there are action-reaction force pairs. Take, for instance, a moment that you're boating in water, in calm water, and we'll say that in this frame of reference that your velocity is 0. You're just sitting there. Maybe you're fishing. And Benny pops up out of the water. He's wearing some flippers. He's been snorkeling. And he's got his friend Scorpion with him. So what Benny does is Benny tosses his Scorpion up to you because Benny's a sharing kind of guy. And you are terrified of the Scorpion, therefore you are going to apply a force to the Scorpion. Right? You're going to apply a force to the Scorpion to throw it away out of your hand. So that means that in this case, if we can neglect air resistance, the net force for the Scorpion is going to be equal to the mass of the Scorpion times the acceleration of the Scorpion. But according to Newton's third law, if you apply a force to the Scorpion, then the Scorpion is going to apply a force to you in the equal and opposite direction. So the net force of you, remember you are attached to the boat, so this is going to be the net force of you and the boat are going to be equal to the mass of you and the boat times the acceleration. So that means that in this case, if we can neglect friction between the boat and the water, and we can neglect air resistance for the Scorpion, then that means that in this case, the net force for both of you is going to be equal. But let's consider the action, because the motion that occurs is going to be proportional to the net force and the mass. And here the Scorpion is very small, so when you apply a force to the Scorpion, it's going to accelerate away from you and then travel away with a large velocity. You and the mass of the boat are much larger, so that means that you will also accelerate away, but your acceleration will be much smaller. And so this is a very simple reaction pair that we could take a look at. This is a Newton's third law situation. There's another situation, and that would be a rocket launch. So let's say Benny and his friend Scorpion decide to take off to space in a rocket. A lot of people think that the force that causes the rocket to accelerate from the ground is a push against the ground. But in the case of a rocket, it's actually the fact that there's a combustion happening that's causing the liquid rocket fuel to expand out into a gas, and it's being squeezed through a very thin pipe. And that means that the rocket is applying a downward force on the gas. And according to Newton's third law, the gas is then applying an equal but opposite force upward on the rocket, causing the rocket to accelerate upward as long as there is a force on the gas. And that's why rocket propulsion works in space as well, because you don't need there to be air or matter or a ground surface in order to apply a force to the gas. All you need is for there to be a pipe and an expansion of the gas that causes the gas to be forced backward, and the rocket ship will move in a forward direction that's opposite to the direction that the gas is being forced. That's a really cool discovery, and it's thanks to Isaac Newton that we're able to do those sorts of manipulations and maneuverings into space. This is how we get our satellites up into space, so you could say thanks, Newton, for your cell phone. There are more situations that we can consider with Newton's third law. And let's go ahead and let's take a look at conceptual example 4.4, driving your car. So have you ever stopped to think about what exerts a force on a car? And let's take a look at Benny and his car. Alright, well, the first thing you might think is you might think that the engine is what's exerting the force on the car. But the engine is not in contact with the ground whatsoever, so how can it make the car move? What the engine does is the engine applies a force on the axle. The axle turns the wheels, and what ends up happening is the wheel applies a backward force on the ground. As the wheel turns, the portion of the wheel that's in contact with the ground applies a backward force on the ground. And if you've got four-wheel drive, it happens in both situations. The wheel applies a backward force on the ground. As a result, the ground applies an equal and opposite force on the wheels, causing the car to accelerate forward. How do we know that this is the case? Well, imagine, if you will, putting a car on a friction-free surface where the ground does not have friction, and so a backward force cannot be applied to the ground. In that case, the wheels would spin, they would not catch, and the car would not go anywhere. This is why if you get stuck in the mud, or if you drive out onto ice, or if you put a vehicle on a slip surface, no matter how hard you press on the accelerator, no matter how much force the engine applies to the axle to move the wheel, the car doesn't go anywhere. It must be able to apply a backward frictional force on the ground in order for the ground to propel the car or accelerate the car forward. And so that brings us to the thought. Here we have the ground accelerating a car. What we usually think of when we think of forces is we think of active objects. But the truth is that resting objects can apply forces too. A wall can apply a force, much as it did in our ice skater example. Desks can apply forces, as in the situation of every time you put your backpack on a desk or push off of a desk. Inanimate dead corpses could apply forces. All they have to do is to be an action-reaction pair. think of a situation, we've talked about like, oh, I can apply a force to a wall and I don't see the wall accelerate. And one of the reasons for that is that there's more going on than just your force when we talk about the net force of a wall or a desk. And the other has to do with the fact that a lot of the times we think of things as a simple spherical cow model, when in reality, just like the ball of clay that we discussed last Friday, objects have molecules in them, and those molecules can react a little bit differently. And so what we can talk about there is we can talk about the fact that there's some compressibility in large inanimate objects, even if we don't see that compressibility, right? If you pulled back on a rubber band, that rubber band would stretch, and then it would apply a force in turn, right? The same with the bungee cord. You stretch a bungee cord, and the bungee cord provides a resistive force. Well, even hard surfaces like desks, they have some compressibility to them, and that compressibility is responsible for those forces that inanimate objects can apply or experience. And so back to this idea that tends to be the largest struggle with Newton's third law. And that is that it's important to remember that a force only influences the motion of the object it acts on. And we said that it takes another object to apply a force on an object. So here, I give us two words to really help us think through this situation: on and by. When we talk about a force on an object, right? A force that acts on an object, this will influence the object's motion. When we talk about a force exerted by an object, this will not influence an object's motion. And this is incredibly important, because when you're deciding what forces to include in your net force, all right, you must remember to only include the forces that are acting on an object. If you're pushing and you're the object that you're trying to determine the net force for, you will not include your pushing force. So when we consider, right, a force, you push wall. Alright? What happens is this force is equal and opposite to the force of wall push you. It's equal and it's opposite. Therefore, the force that you push the wall with is equal in size to the force that the wall pushes you with, but opposite in direction. Alright, so that means that when we do the net force for you, right, which force would we consider? Well, the net force for you is the force that you are experiencing. It's the forces on you. So the net force of you would be this one. Alright, it would include the force that the wall pushes on you. It would not include this one, because this is a force by you. This force would be included in the net forces on the wall. Alright, this one is included for the wall. Alright, you experience one force, the wall experiences the other. There's no way for you to experience both the force you apply and the force you experience. It's never going to happen. So that brings us to conceptual example 4-5. Benny has a very large slab that he has asked you to move in a sled that he built himself. You feel like there's no way that you're ever going to get this large slab to move in the sled, because you understand Newton's third law. You say that for every action there's an equal and opposite reaction. So if you apply a force to the sled will apply an equal and opposite force to you, and that means that there's no way that you're ever going to go anywhere. And Benny says, no, trust me, you can. So let's consider all forces acting on you in brown, and all forces acting on the sled will do in blue, and any forces acting by a third-party object in red. So, alright, you pull on the sled. The sled pulls on you. These forces are equal and opposite. You can only experience the force on you. You don't experience this force pulling in that direction. All right. What else is happening? If we're going to do the net forces of you, all right, what other forces are you experiencing? Well, it turns out that you are pushing on the ground in order to pull the sled. And the ground is pushing on you. Therefore, your net force is going to be a result of the force of tension on the string that you're pulling, and it's going to be a result of the force that the ground is pushing you with. Right? And so we have to decide, just like we would in any circumstance, what our axis system is going to be. I'm going to go with traditional, which means right is positive, left is negative. So your net force is going to be the force on the ground minus the force of tension that the sled is resisting you with. Which means that as long as you push hard enough on the ground, right, you will experience a net force in the positive direction, causing it to accelerate. Now, let's consider all of the forces that the sled is experiencing, because the sled is experiencing this pull from you, but the sled is also having an action-reaction pair with the ground. The sled is pushing back on the ground, which means that the ground is pushing forward on the sled. Okay. So what that ends up meaning, it means that the net force of the sled is going to be a result of what the sled experiences, which is the force of tension from you. In this case, it's positive, and the force from the ground. I should have been opposite. Right? The ground experiences this force. The sled experiences this force. I got my colors mixed up. Which means that the net force of the sled can be in the positive direction. And what it comes down to is that you have the ability to accelerate the sled because you're only experiencing your net forces, the force that the sled applies to you, not the force you apply to the sled. And the sled only experiences the forces acted on it. The force acted on it by you, and the force acting on it by the ground. And so, last but not least, when we talk about forces, I would like to bring up the idea of a bug hitting your windshield. So, here we've got Benny driving your car again. And he's speeding. He's got a very large velocity. And what ends up happening as a result of his very large velocity is this very nice and innocent butterfly is going to hit the windshield. So think about what's going to happen. Right? The butterfly is traveling this way. Benny is traveling this way. And once they collide, Benny is going to continue traveling in that direction with a squished butterfly on his windshield. How is that possible if the force experienced by Benny and the butterfly are exactly the same? Well, it turns out that it has everything to do with this idea that force equals mass times acceleration. Right? If we say that the force on the butterfly is equal and opposite to the force on the car, then one thing that I know is I know that the force on the butterfly is going to be equal to mass times acceleration of the butterfly. Mass of the butterfly, acceleration of the butterfly. And I know that negative force on the car is going to be equal to the mass on the car and the acceleration on the car, which means that the butterfly is going to accelerate in one direction and you are going to accelerate in the other. And I'm going to do just a quick change of my signs here. Right? What happened is that I think about Benny moving this way means that Benny's force is going to be applied in the right direction. The butterfly's force is going to be applied in the left direction. So I'm going to make the butterfly's force direction negative, the car's force direction positive, which means that the butterfly is going to have a force experience in the negative direction and acceleration in the negative direction, acceleration, and the car is going to have a force in the positive direction and an acceleration in the positive direction. Doesn't matter. Now, let's think about that acceleration. Right? The force on the butterfly and the force on the car are equal. They're just in opposite directions. The mass of the car is gigantic. And the mass of the butterfly is tiny. Force equals mass times acceleration. So if we think about the relationship between acceleration, force, and mass, then we know that it would take a tiny mass times a really big acceleration to equal a force that's the same as this force. Which means that if I take the force that the butterfly experiences and divide it by a really tiny mass, I'm going to get a really large acceleration. That butterfly not only came to a stop, but it came to a stop and then it accelerated in the opposite direction until it was traveling at the same velocity of the car. Its guts splattered all over the windshield. On the other hand, the car is really, really big. So if I take the force that the car experienced, which is the same as the force that the butterfly experienced, but in the opposite direction, right? That means that this mass here was really, really big, and in result, the acceleration was tiny. In fact, it was so tiny that it wasn't experienced by the car at all. It, in fact, could have been taken account for just in the elasticity or the bounce of the windshield. So that is how a bug hitting a windshield can be experiencing the exact same force as the windshield experiences from hitting the bug. And it has everything to do with the fact that even though the forces are equal, the masses are very different, which causes the accelerations to be very different. And another thing to consider is that the actual experienced acceleration of an object is due to the net force, and the net force is likely going to be different for this butterfly that is flying in the air and the car which is driving on the ground. So hopefully after this lecture you feel more comfortable with the idea of Newton's third law and how things can actually still continue to happen, even though Newton's third law says that forces on objects are equal and opposite. And it has everything to do with the fact that the forces are equal and opposite, and that's the force that's coming in the pair, but it doesn't mean that net forces that objects are experiencing are equal. It also means that objects can only experience forces that are acting on them, not the forces that they are using or applying. And it also means that an object's mass and the overall net force that an object experiences all matter when it comes to taking a look at the motion that any object experiences.